Hello friends, and welcome. Imagine you are a university administrator, trying to figure out how many students are enrolled in math, physics, or computer science. Some students take 2 of these courses, some take all 3, and you need to count without double counting anyone. This is exactly the kind of problem that set theory was built to solve. In this video, we are going to walk through 3 powerful tools from discrete math. Venn diagrams, which help you visualize sets and their relationships. Partitions, which let you cleanly divide a set into non-overlapping pieces. And power sets, which capture every possible subset of a set. These 3 ideas are deeply connected, and by the end, you will see exactly how. Let's get started. Alright, let's build our foundation. A set is simply a collection of distinct objects, called elements. We can visualize relationships between sets using a Venn diagram. Here we have 2 sets, A equals 1, 2, 3, and B equals 2, 3, 4. The left circle holds all elements of A, the right circle holds all elements of B, and the overlapping region in the middle is where they share elements. The union of A and B, written A union B, contains every element that is in A or B or both. So A union B equals 1, 2, 3, 4. The intersection, A intersect B, contains only elements in both sets. That gives us 2 and 3. The complement of A contains everything in the universal set U that is not in A. These 3 operations form the core vocabulary of set theory, and Venn diagrams make them instantly visible. Next, let's use these ideas to solve a real counting problem. Now let's put Venn diagrams to work. Suppose set A has 25 elements, and set B has 20 elements, and we know that 8 elements belong to both. How many elements are in A union B? If you simply added 25 plus 20, you would get 45, but that double counts the 8 shared elements. The inclusion-exclusion principle fixes this. The formula says the size of A union B equals the size of A plus the size of B minus the size of A intersect B. That gives us 25 plus 20 minus 8, which equals 37. Now look at the diagram. The left-only region has 17 elements, the overlap has 8, and the right-only region has 12. Add them, 17 plus 8 plus 12 equals 37. The diagram and the formula agree perfectly. This principle extends to 3 or more sets, and it is one of the most useful counting tools in discrete math. Up next, we shift from overlapping regions to cleanly separated ones with partitions. Here's the interesting part. Sometimes you want to divide a set so that every element lands in exactly one group, with no overlaps and no elements left out. That is called a partition. A partition of set S is a collection of non-empty subsets satisfying 2 conditions. First, the subsets must be pairwise disjoint, meaning no 2 share any element. Second, their union must equal S, covering every element. Look at the example. S equals 1, 2, 3, 4, 5, 6, split into A1 equals 1 and 2, A2 equals 3 and 4, and A3 equals 5 and 6. The 3 subsets share no elements, satisfying condition 1. Together they cover all 6 elements of S, satisfying condition 2. Both conditions hold, so this is a valid partition. Now let's look at a concept that collects all possible subsets, not just disjoint ones. Let me show you one of the most elegant ideas in discrete math. The power set of S, written P of S, is the set containing every possible subset of S, including the empty set and S itself. Let's build it for S equals A, B, circa. First, the empty set. Then the 3 one-element subsets, namely A, B, and century. Then the 3 two-element subsets, namely A and B, A and C, and B and century. Finally, the full set, A, B, circa. That gives us 8 subsets in total. Why 8? Because for each element, you make a binary choice. Include it, or leave it out. With 3 elements, you have 2 times 2 times 2 choices, which equals 2 to the power of 3, which equals 8. In general, if S has n elements, then P of S has 2 to the power of n subsets. So for a set with 10 elements, the power set has 1024 members. Up next, let's connect all 3 concepts and see how they fit together. Alright, let's bring it all together. These 3 concepts form a connected family of ideas. Every partition of S is a collection of subsets of S, so it lives inside the power set of S. It is a special subset of P of S, where the pieces are disjoint and cover everything. Venn diagrams give you a visual language to see both. Overlapping regions show unions and intersections, and non-overlapping regions illustrate partitions. 3 rules to carry with you. The inclusion-exclusion formula. The size of A union B equals the size of A plus the size of B minus the size of A intersect B. A partition requires subsets that are disjoint, non-empty, and whose union equals S. And the power set of A set with n elements has exactly 2 to the power of n subsets. Try this. List all partitions of S equals 1, 2, 3. Thanks for watching, and see you in the next video.